everyone, welcome to Under the Microscope. I'm your host, Pranoti Kshirsagar, and today we have with us yet another QuanTour Hero. And this time we have the guest from Paris. Please join me in welcoming Pascale Sellenart. And now get ready for the list of things Pascale is doing. Other than the research aspects, okay? We will come to the research aspects of her life as a scientist in this podcast, but also other things that she's doing. Let me start with Pascale is a research director at the Center for Nanoscience and Nanotechnology, CNRS, at the University of Paris-Saclay, that's in France, of course. She is also an associate professor at the École Polytechnique, which is another institution also in Paris. And in addition to this, she is also on the French Presidential Council for Science, Presidential Council, France's Presidential Council, and there are more things coming. So hold your coffee while I get her on to talk about her research and her life as a scientist. Pascale is also the co-founder of Quandela, which is a company, and we will talk about that as well in this podcast. And she is also the member of the French Academy of Science, which is like all of this. I don't know how she's doing it, but we will figure that out. With Pascale, we will ask her all the questions and learn about her research. And she's also the only hero on the QuanTour tour who is actually doing the quantum computing, so the information processing with the quantum science. So please join me in welcoming Pascale. Hi, Pascale.
Hi, very good. Thank you for this very kind introduction. How are you?
I'm good. I'm so excited and pumped to talk to you, to learn about your research. And let me first ask you, how many hours in the day do you have to do all of these things?
It's good that I had my children very early on. So now I have a lot of time to dedicate to all these positions you were discussing, you were presenting, and actually kind of my passion, okay, in life. I would not be doing all that if I was not enjoying myself, clearly. But I won't count the hours because this is the part that I'm not doing so well. I should have more personal time, for sure.
I understand. So you're not just doing the research, you're also on the business side of quantum science, so being the co-founder of Quandela, and also involved in the political, like more on the advisory side of things,
advisory,
of course.
Advisory, yeah.
It's just like the Presidential Council for Science.
Yeah. It's just advisory role, yes, for sure.
Advisory role. So you are doing everything. So societal, business side, research side, everything.
Yeah. And I really love the combination, at least of the first two, science and industry. I think it's fantastic. Okay, I'm 52 years old. Huh? I have been doing this research for 23 years, 20 years, yes. And it's really satisfying for me, at least, that 7 years ago, we decided to take this bit of research that I had been conducting for a decade or so and turn it into something that becomes a product and that launched a completely new adventure. We basically, in this QuanTour, we discuss quantum dots with semiconductor devices that emit photons. And on my research path, we fabricated very interesting and efficient single photon sources that became useful for quantum computing. So I have been somehow already in contact with the community, the scientific community developing quantum computers for more than a decade now. They came to me early on saying, we want this stuff we want your devices to play with. And we're like, they're not good enough. So yes, please make them better. Okay. And we did that. And I feel extremely lucky because of this, meeting these people needing very specific stuff from our devices. It pushed my research in some direction. And I would probably have not thought of myself, that I would not have probably pushed so hard, because when you're doing something in research, when it works 80% of the time, it's cool. But for industry, it's absolutely not enough. And actually on the way from 80% to more, there is a lot of very interesting science that I would not have anticipated. So I feel extremely lucky to be in between these two worlds. And then now with Quandela, I'm not only working as a physicist, I'm working with computer scientists, people doing math, application engineers, and it's really cool.
Oh my God.
I'm having the best time here. Typically, it's the most fun ever, really.
Oh, that is so cool. That is so cool. That is so cool. I'm going to ask you a lot more questions, also the science behind the Quandela as well. I want to know that as well. But let's start slow, right? Let's start with understanding your research.
Yeah.
The research that you're doing at the CNRS as a research director at the Nanoscience and Nanotechnology Center at the CNRS at the University of Paris-Saclay.
You don't have to say that all the time. You can say C2N.
C2N.
Yeah,
C2N.
it's fine.
C2N, CNRS, Paris, France. Great. And then also École Polytechnique. So do you have two different...
Polytechnique, I'm just teaching.
It's teaching, okay.
I'm teaching quantum physics, quantum mechanics. What is amazing about this teaching is that whenever you teach, whatever the level you teach, you have always a student asking you stuff that you didn't think of. And actually, you can be unsettled, and it makes you progress on your understanding.
Absolutely.
Actually, I didn't teach at the beginning of my career, and I think it was really good that I could find time to teach at some point. It changes everything.
That is absolutely true. So tell me about your research now. I want to enough with the I want to know the research now. What are you doing?
So what am I doing? We are working these quantum dots. You've heard about them. So just in a sentence, it's basically semiconductors. You can consider it as like 10,000 of atoms that just behave like one. They behave one. It's as if we had taken an artificial atom, we engineer it. So you heard about Armando, who grows Rinaldo, who puts strain on them to control their properties, etc. So on my side, what is very specific to my group is that, so in nature, if you want to produce the quantum of light, the photon, a drop of photon, the natural system that emits photon is an atom. But it's very hard if you want to just trap atoms, just an atom in vacuum. It's very complicated to do. So what is fantastic with the quantum dot is that you can use the tools of micro and optoelectronics with a clean room, and you can grow this artificial atom, and then you can actually sculpt the matter at the micro and nano scale to define their environment. So what is very specific from my group is that we have been working for 20 years now on how to force this atom to emit in a given direction. Because an atom emits one photon at a time, but the photon is emitted in all the directions of space.
Correct, yeah.
And if you want to use the photon, you need to collect the photon to have it somewhere. So ideally, typically in one direction, and even better in an optical fiber, so that you can take the photon and bring it somewhere else. And so there is a fundamental paper, and a beautiful one. Actually, it's fantastic because it's 20 lines. The scientists, 20 lines. That's it. Purcell, I don't remember the year now, but in the year 40s, wrote these 20 lines to explain that if you put an emitter, so an atom, and you put it in between mirrors, you change the way it emits photon. It emits light. So basically, the idea is that the property of emitting light is not a property of the atom only, it's the property of the atom and what's around it.
The environment as well.
Yes. And so we can sculpt the environment, we can design the environment and put the atom in what we call an optical cavity to make sure that the photons are emitted in one direction. So what is very specific in my group is that, so this idea has been in the air for 20 years, but what was very specific, what we did here is that we need the atom to be very precisely in this cavity. So you have two mirrors, for instance, and you want the atom to be exactly there in the middle and exactly at the good energy compared to the cavity, for instance.
True.
And you have learned from the previous podcast that when we grow quantum dots, they kind of form spontaneously. We don't know how to make them be here or there. And even all of them are a bit different. So if you think of that, I have like fantastic single photon emitters, but they are randomly in position and space. And I want them here in between my two mirrors precisely. How do I do that? So this is what made a big step for my team, is that in 2005, I had an idea on how to do that. I remember well because I was visiting a laboratory in Southampton, and I remember seeing something. I was like, I have an idea. And so the idea was that we measure optically the position of the atom. I don't know where they are, but I can have a very extremely precise measurement of where the atom is. And I can at the same time do what we call a photolithography step, which is actually the step you do to define the cavity. So basically, we start with the atom is somewhere in the sample, and I want to etch just around the quantum dot. And to do that, I need to know where the quantum dot is. And I need to also to know at which wavelength it emits. So basically what we invented back then was to measure optically and do a lithography. Lithography means that we shine a laser on some kind of polymer, and this laser changes the property of the polymer. And basically what you are doing is that you are just drawing with a laser a circle exactly centered on the dot. And then with that, then we etch a pillar that is where the dot exactly is. So we did that in 2008 for the first time. And it was one of the very first paper that allowed to have many devices where each time there is a dot exactly where I want it, in the middle of the cavity and exactly at the right wavelength. And that was a turning point, I would say, for my research.
I have so many questions, Pascale. Sorry.
Okay.
I have so many questions. So you mentioned you did the location, like you drew like a circle around and then you etched it. That basically for people to understand, like scooping ice cream out.
You dig around and you remove everything that is around and you keep only where your emitter is and that the mirrors around it.
Exactly. Where do the mirrors come from?
Yeah, so basically what we can do with the semiconductor technology is that you can grow atoms layer by layers. Okay? So what Armando has explained is that when you try to grow layers of atom and they don't have the same crystal
lattice,
then structure lattice, then we can create the dots. You can do that. But before that, you can grow crystals lines of atom and you can alternate two materials. We alternate aluminium arsenide and gallium arsenide. And when you do that, actually, we are piling up layers of different refractive index. And this is a mirror. So you pile up mirrors with refractive index and you grow the quantum dot. And then you pile up another mirrors with refractive index. And so it all makes two mirrors with a dot in the middle. So it's just, for now, it's 2D, like this. And then I find where the dot is and I etch to have a mirror on top and mirror at the bottom. And then the cylinder confines light in the other direction, like in an optical fiber.
Oh, wow. Because the cylinder, the walls, the inside walls of the cylinder, the hollow cylinder, these are your two layers that
vertically you have the mirrors, and laterally you can think of it as in an optical fiber. You have just a cylinder of high refractive index that guides light. So it's also a mirror. So this is a very old geometry, but what was very new was the possibility to really know
the quantum dot there.
Exactly there. Oh, and so we have been doing that for 16 years now, and it changed everything because now we control our devices. It's a game changer when you want to do some kind of systematic studies to understand what's going on and etc. Right. So this was the first turning point. And then the second one was, I think, when we started to have very bright single photons. So in 2013, we could show that whenever we press a button, so we excite the dot with a laser, and it emits a photon, we could collect the photon with 80% efficiency. So that was huge. And it is the moment where I started to be contacted by leading groups in quantum computing. So I can name, the first one contacting me was Andrew White. He's really a founder, is in Brisbane in Australia. And he's really a founder of the field of quantum computing with photons, quantum information processing with photons. And he came to my lab and I said, look, I want to, it's amazing what you're doing. I was like, wow, cool, thank you. And he became, for me, he's just a tiny bit older than me, but he was so much more experienced in quantum computing. He became some kind of a mentor to me, like, Pascale, you should do this, that's great, you should do that. And so he's a fantastic person to work with, trying to always put synergies together. And he pushed me to make not only the sources bright, like we were doing, but to make them, what we say, indistinguishable. So generate always the same photon. I don't know if it was discussed on the podcast before, the indistinguishability.
We did cover it a little bit, I think, because it's important to have this quantum communication, because then the quantum dot has to be, like, the emission should be similar. But please explain it. Please.
The idea is that you want the photon to be completely identical, because if you have that, then there is a beautiful quantum phenomena that take place. Is that if you take two photons that are completely identical and you send them on the beam splitter, so you can think of that as a crossroad. They come from different roads and then they cross the roads. And in the classical world, there are four possibilities. Each photon goes straight or turn. But in quantum physics, if the two photons are completely identical, they will also either cross or turn, but always together. So it's going to be, I'm coming with you or I'm coming with you. And they come together out the output. And they come together on both roads. So it is a way to create what we call an entangled state.
Where the entangled state. Yes.
Yes, it's an entanglement, and it's an entanglement, what we say, it's an entanglement in path. It means that they are either both on one side or either both on the other side. And if I measure one of these sides, I know that the other one is here too. And if I measure the other one on that side, I know that the other one is here too. Okay? And that's extremely powerful for quantum information processing because you want to create entanglement.
Absolutely.
Okay. Yeah. So this was 2012, 13, and then we started to have good indistinguishability, like 80%, but as I said, they want 99. So then in the next 3 years, we worked a lot on making this photon more and more indistinguishable. So what does it mean to have indistinguishable photon? It means that each time the dot emits, we want the photon to be exactly the same wavelength, same shape, same polarization, etc. And what can influence that? What's around the dot? If around the dot, there are other charges that are floating around, they make some kind of random electric field and it changes the wavelength of the dot. If the dot is in a crystal and the crystal, the atom can vibrate, this is a phonon, you can have some acoustic wave. And that, of course, will influence the photon that the dot emits. So in the next 3 years, we worked on making the environment less noisy to some extent. And in the end of 2015, and this is the beginning of Quandela's adventure, we managed to have not only efficient sources, it was no longer 80%, and it was like 20%, but now the photons were like 99.5 identical. And then it changed everything. Then it was really cool because the PhD student and postdoc who were working with me at that time, their name is Valerian Gies and Nicolas Somaski. They are now the CEO and CTO of Quandela. They were going in conferences and everyone was like taking pictures. We're like, wow, 95, 99.5. And it was really it was a fantastic feeling. You go around, you present your result and researchers like, yes, I want your source. It was really cool. So then my adventure, my scientific path became different because I had now two paths. Nicolo came to me and said, let's create a startup. I was like, are you crazy? But I took advice from an old friend that I can mention here because he's another one of my mentor. His name is Khaled Karay. And he created a company that is very famous for us, nano quantum scientists, which is, the name of the company is Atocube in Munich. They make a high-level precision scientific instrumentation. And he created this company in 2000, in the beginning of the 2000. And so I turned to him to say, is it a good idea? What do you think? And we discussed and he said, yes, it's an excellent idea. You should do that. And so actually he helped us start the company and his partner now. And so then from 2015 onward, we said, okay, I will keep my research work, but I will also be on the adventure of Quandela. Yeah. So Quandela was created in June 2017. So it's been 7 years now. At the beginning, there were 4 or 5, and now it's 100 people.
That is so cool. That is so cool. Oh my God. Okay. Thank you for explaining also the history of how it came to your current research, so to say.
I didn't get to my current research yet, but...
right, because I'm still waiting for the computing part.
Yeah.
Okay, where is this coming with the computing part? But this is...
It's coming down.
Just to recap, yeah? So... you managed to, together with your team, of course, you managed to do like the isolation of the quantum dots, or rather identifying where the quantum dots are on your substrate, digging a tunnel or a hollow cylinder, so to say, making like the tower, yeah. Make sure that there is the mirrors who make sure that the photon is emitted in the direction that you want it to be emitted. So to align it with this nano mirrors, micro mirrors, atomic mirrors, something like that. And then we continue developing it. And now you have reached the point you're together with the team, you have managed to get to the 99%, 99.2, something like that, very high.
High indistinguishability, yeah.
Yeah, exactly, which is extremely important, especially when we are talking about using this technology in real life.
Technology, exactly.
Exactly. So that's where Quandela also came in. And this is, I'm going to ask you the names, like the correct names and maybe the websites and everything to be to the description and also to the captions of this video for anyone who is watching on YouTube or who is listening on Spotify or Apple Podcasts or wherever, to add the names and the descriptions in the show notes, of course. Okay, now coming to I want to understand, because so far I feel like it is with the material that you're doing. So there is a lot of, let's say, lab work, so to say, but how does this now connect with the computing part?
Computing is a hardware machine that allows you to do some complex computation. Okay?
Correct.
You cannot do it with pencil and the paper. Okay? So a computer is a hardware first, and then there is software, etc. So when we jump to computing, so as I said, I was contacted by all these people who wanted single photon sources, and there were these groups. So I have a very excellent collaboration with Andrew White, and then Agay Eisenberg from Israel, and then Fabio Schiareno and Roberto Zelame from Rome and Milan. And they all wanted to play with single photons. And so it takes some time to turn a lab demonstration into a product, okay? So we decided to create Quandela, but we were not ready to immediately sell the sources, okay? In the meantime, what happened is that we started working together, so in a collaboration between my lab and their teams. And this is when we started to play with the photons themselves. And then we use this effect that when they come together on the beam splitter, they exit together, to do first small-scale protocol with 3-4 photons of what we call quantum information processing. So basically, you take the photons of a source, and then you send them you don't have a bulky beam splitter. You make a photonic circuit. Everything is integrated. It's like a waveguide, and they come together, go apart. And so you have a circuit. For instance, some of them are made by the group of Roberto Zelame in Milan. And you couple my sources where they're cheap, and then we come up with an idea, some protocol, then you put detectors and you do a measurement, and it's a first proof of concept of computation. We've been doing that since 2016, 17 in my group. And then Quandela was ready to commercialize the sources around 2017. So the first source was sold actually to Andrew White, my first friend now in quantum technologies. And now I would say they have sold maybe a dozen of these sources in all the leading groups of quantum computing. So this is where we were in 2019. Then COVID came, and then the ecosystem of quantum changed. There was all this quantum hype that came in. All the politicians realizing that, oh wow, quantum is important. Yes, it is indeed. And it's actually very important. It can be a game changer. It's a game changer. We don't know how long it's going to take to come up with big application. That's really a game changer. Then we realized, Nicolo, Valerio, and I, the co-founder, that first we created the company to sell a device that was useful during quantum technologies. But then quantum technologies became also a business. And we understood that actually those who would be developing the machine, the quantum computers, will not be in labs anymore, but they will be in companies. And also we decided that we want to be one of these companies. So in 2020, we hired a theoretician of Shane Mansfield, who has a beautiful track record in quantum information on the theoretical side, and to join. And we were very happy that he joined, and we could have in Quandela not only hardware, but also algorithm. And then what was missing came end of 2020, beginning of 22. And is a computer scientist. Because in the end, it's a computer, so it's better to have also computer science. So it's not the same to be a computer scientist and doing algorithm. It's not the same people. And that person is my husband. He joined the company. And so now we have all the technical expertise to really build the first computer. And we actually built this first computer. It was put on the cloud at the end of 2022, beginning of 2023. So we assembled a machine that took the beautiful quantum dot single photon sources, inserted them in some kind of plug and play architecture. That's the hardest part. It's so hard to do that, to make things work in a suitcase-like stuff, and then integrate all that with all the components to build the first quantum computing machine. And this machine has been on the cloud for 2 years now. So this is where I started to do also quantum computing protocols, which was really cool. And I learned so much doing that. But the science and material side is with quantum dot is not finished at all. Because we know that we need entangled photons, more efficient entangled photons.
From proof of concept to now already having the product out in the market since over a year, since 1.5 years. This is brilliant. So is this the kind of, can I use it like as a private person? Can I buy it? And
no, so you cannot buy the computer, but you can have time. You can have some free access to it so for academics people. There is some kind of free access for some. It's like every other computing company. There is always an open version that's more limited in terms of computing power and some slot of time. If you want more times, and especially for industrial, they have to pay.
Yeah, of course.
But as an individual, we have many students who have learned to play with it. It's a Python code that was developed. It's a framework. It's becoming a reality. Okay.
It's
the interesting side, and I still have to tell you stuff about the research side to some extent. But
yes, we will get to that. But I would love to play with the thing as well. I'm not a student anymore, but I would just like
to play with it. I'm saying students because we have some time including this kind of education in the university program, education track to program on the quantum computing machine that are available, including ours.
Oh, that is so cool.
Yeah,
please pictures of that. Please pictures of that. Please. I want to see it. I want to see where the magic happens. Okay. Research. Let's talk about research.
So the research didn't stop when we created Quandela at all. Actually, I would say that because we had now Quandela doing a lot of engineering, we had better sources, better devices, better systems, and actually we pushed further the research. So let me mention two things I am very proud about. The next stuff that we have been investigating, we need to have the dot emit not a single photon, but many entangled photons, like a chain of entangled photons. How do you say that?
A pearl, a necklace.
Yeah, a pearl necklace. Yeah, but it's photons, one after the other, that are all entangled together. And the way to do that is to exploit what you call a spin. So you will hear about the spin in quantum dots a lot when you will have the podcast with Media Tature. You can have in the quantum dot an electron, for instance, and the electron has what we call a spin. So it's like an intrinsic nanomagnet. The magnet is pointing in this direction or in this direction. Actually, the dot will emit a photon that goes like this. And if it's like that, it's going to go like that in the other direction in terms of polarization. And what we have shown 2 years ago, yes, it was published last year, but it was shown 2 years ago, is that now we can actually use this spin to create photons that are all entangled by spin like that.
Spin up or spin down. Yeah.
It means that with the same devices as before, we create not only single photon, but chains of photons. And this is a game changer for quantum computation, because this is what we need to go toward what we call error correction, fault tolerance.
What correction again?
But whenever you build a computer, even the classical one, they can make errors. And you need to correct the errors. And the way to correct for errors in quantum computing is to have some kind of algorithm that exploit more qubits. We talk about a qubit that is a logical one, a good quality qubit. You can build it from a larger number of individual qubits. So basically you can take, it's not the right number, but maybe I need 10 photons, a good logical qubit.
One logical qubit. Huh?
And a logical qubit is a qubit that is corrected for errors and requires a kind of state that we are generating, the entangled photon state. Yeah. So it means that this is an important next step that we have developed in the last years, and it's very important for computing. And the other stuff I want to mention, because it brings me back and I love it, it's to fundamental science. We also, with another PhD student and a colleague who's now in Singapore, Alexia Ofev, we wanted to investigate what it means to do energetic exchanges at the quantum. In thermodynamics, it's about the property of temperature. So temperature, what is it? It's how many particles, they move in all directions. The faster they move, the higher the temperature is. What does it mean to have temperature or heat in a quantum system? Does it even have a meaning? Okay. So I know nothing about that, but there is a community of theoreticians working on that, trying to understand what it means to have work and heat, etc. And so we did a study with our system to understand what it means to exchange energy between the quantum dot and the electromagnetic field when it emits a photon, to try to understand what are the different types of energies that are exchanged. So you see here, it's just fully fundamental research, no application for now, but it's possible because of everything we've done before as well. So I'm not an industrial researcher. This is the best. This is the most fun because I've been doing that, I understand more other things. So this is really an opportunity.
This is so cool. Oh my God. I feel like I could talk to you about this because I have so many questions. I have so many questions. So many questions. But I'm going to ask you one question, which is probably, I think you are the best person to answer that question because you're also doing the computing as well. I'm asking you on behalf of all our listeners and followers. When you think about this quantum computer, there's this golden sort of lots of wires, like that is the image that you usually find. Yeah, so there is the chip in the center and all the golden pipes or whatsoever. These are basically to cool this particular chip, right? That is how I understand it. Is that correct? And does your quantum computer look like that? Or that's why I was like, I want to see your picture now.
The image you have in mind is the quantum computer from Google, superconducting quantum computer, where everything is cold and all these wires are wires to control the chip that is at minus 270 degrees, etc. So we are not looking, it's not always like that because in our case, there is a cryostat, there is a fridge to cool down our dots, but it's very different because actually it looks like a rack. And if you look inside, you have devices of quantum dot that we discussed. Yeah, there is a fiber on top of it. It's all included in some kind of sealed chamber. This is in the cryostat. In the cryostat, we have also other detectors there are also a fiber on top of it. All this size box, like a suitcase size cryostat. And the rest are just drawers with integrated chips and fibers everywhere. Fibers and a bit of electronic controls. And that's it. And it doesn't look at all the same. And what is very different is that what we call computer architecture is that extremely modular. We combine the sources with the chips, with the detectors, and we can remove the chip, change to another chip, more detectors. It's extremely modular. And it's a very different approach. And it's one of the approaches that requires a less of cooling down.
Okay, so that's good. That's good.
It's a cryostat. It's a fridge that you plug on the wall with a normal plug. Nothing special.
Really?
Yeah, it's cool.
Oh my God, that is so cool. And it's like almost like a Lego. Okay, today I want to use this chip, tomorrow not at that frequency.
It's exactly that. Not today, but every month. If you want to change the chip, to change the application, you can have chips for specific application. You can increase the number of modes on the chips, stuff like that.
Okay. Interesting. Super interesting. Wow. Okay, Pascale, I can continue asking you so many questions, but let me now go back in time a little bit together with you and understand your career journey. Where did it all start? Did you come from this? Were you just born with, okay, quantum computing, here we go? Tell me about your career journey so far.
I don't come at all from a scientific family or at all. My mother was a teacher. My father left school very early at 16 years old or something like that. And he engaged in the army to learn electronics. This was a long time ago. And he became a technician and then an engineer, but like a self-made man away from any school or university. Anyways, my grandparents were winemakers. And why did I come up doing science is because whenever we were going to visit my grandparents, we were passing by a beautiful place, which is called the Radio Astronomy Station in Nancy, in France. It's one of the very first radio astronomy station in the world. It's beautiful. It's huge mirrors to observe the stars and stuff like that. And when I got 10 years old, we had this possibility in a junior high school to go to do an internship. And I said, I want to go there. And they took me. It was fantastic. They welcomed me for a week and they explained to me everything. It was amazing. And it went well. I was asking many questions and they said, you come back whenever you want. And actually, I came back almost every vacation for 5 years. And it was amazing because as I was growing up, I was going through high school, first year, second year, I was learning more stuff. They gave me more stuff to do. I remember a summer where they told me, can you learn Fortran? I said, yeah, sure. And and then I had a month of internship where I was doing programming for the solar observation. So it was really a unique opportunity. And I knew from there that I wanted to do science. When I got into higher education studies, I knew that I didn't want to do astronomy because it's I thought it was more contemplative. You wait for the stars to show up, you measure that. And then I had amazing teachers at École Polytechnique. Some are very famous. Alain Aspect got the Nobel Prize 2 years ago. Others that you may not know, but I think are equally famous in other domains, like Claude Weisbuch is a founding father of optics in semiconductors. He's an amazing person. And in the end, it's always like that, I think, in science. You meet people and they share their passion and, wow, it's so cool what you're doing. I want to do that. And I did that. And actually, I loved both quantum and semiconductors. And it's so fantastic that there was this research topic of quantum dot that was starting to emerge when I joined the system. And it was the possibility to do exactly that, both of them. And then I watched some of the other podcasts, and my colleagues, they have sometimes travels in different countries. I did not at all, because I had my first child at the beginning of my PhD, my daughter. Then the second one, and when I defended my PhD, I was pregnant with the second one. And my husband was also a high-level computer scientist, and it was too complicated. And we decided just to stay in France and even stay in the Paris area. So wow. Because we needed interesting position for both of us, And when I was lucky, I think it was a different time, but it was okay for me to do that. And I ended up doing even some postdoc in industry. 2 short postdoc in industry, which was actually very interesting because I could realize how different things are done in industry and in the academic lab. And it's equally fun on both sides. It's really differently, but fun. And to some extent that with everything I've told you, I also managed to have both now. Actually, I think it's also shaped my way of doing. There is this thing I want to say, because I think many people don't consider engineering as noble as fundamental science. Yeah. And I am strongly disagreeing with this perspective. I think engineering is what enables fundamental science to go to the very high level. If I didn't have spent some time in the clean room trying to do lithography, I didn't say that, but when we were doing the lithography, we were doing lithography at 4 Kelvin, at minus 170 degrees, okay? It's a bit of a weird idea. When I was doing that, there was nothing noble about it, okay? But it changed everything afterwards for my work. So the idea that technology is as noble, as beautiful as fundamental questions of science, I think is something that I have always brought together in my research. And I think it's really, my trademark, I would say. I love that. And I'm not ashamed of saying I love them both equally.
Yeah, merging them, marrying, because I think it's very important. You both cannot exist without each other. It's exactly.
It's not like there are some like high-level mind that think of very fantastic stuff and the other that do stuff. No, it's just the same. It's just back and forth stuff. And one would not be able to work without the other.
Absolutely. It's also quite interesting that your grandparents were winemakers.
Yes.
That is so cool. What did they think of you pursuing research?
They died before I became a researcher, but my grandfather was still alive when I got to. I was a student at École Polytechnique, which is in France is like the very big thing.
It's the MIT of France, right?
Exactly, and he was so proud. It was really. I was very happy to see how proud he was. Yeah, for sure, it was really cool.
That is so cool. From that to now, also, I feel like you did mention that you didn't travel around as much. Also, it was different times, but you did manage to, even within France or in Paris or in or around Paris, you did manage to not just get experience in the fundamental research, like research at a research institution, but also in industry, which is something which a lot of scientists don't do, not on purpose, but it's just something that they don't do. And through that now, staying in and around Paris, you did manage to bring all the world to Paris. So this is, Paris must be proud.
Well, I think it's okay. We are doing work.
And yeah, you are definitely the ambassador for the fundamental research and taking the technology from the lab bench to the market shelf.
And then technology comes back and allows you to have to address more fundamental questions. It's beautiful.
Exactly. Absolutely. So now you are, just as a recap, you have co-founded Quandela, which has over 100 people now working. You also are leading the research group. You are a research director at the C2N. How big is your group at the CNRS?
20 people, something like that.
20 people.
Yeah.
Okay. Wow. That is brilliant. And also you are on the presidential council. We didn't even mention that. After mentioning it at the beginning when introducing you, we didn't even go there. Okay, let me ask you this question then now, Pascale. And I do get a lot of flack for asking this question to all my guests. If you have to pick one research project that you're most proud of, or the most fun or quirky one, or the closest to your heart, one research project, please can you pick one and explain it to us in simple words in the section we call In Other Words?
I just told you we solved some kind of technology problem and it changed everything.
Correct.
This is what I'm probably one of those things I'm the proudest of. But there is another one I'm really happy to tell you about. When we do this measurement that we were sending 2 photons on a beam splitter, and then we look at if they go out together, we just have 2 detectors at the end of the beam splitter, okay, at the out. Look at the detection clicks. So we look at the click from here and the click from there. Since the photon should always exit together, there cannot be 2 clicks at the same time. So this is a measurement that everyone you have interviewed on this QuanTour podcast that does. Everyone does that.
Correct.
For some years, from the very beginning in 2015, we were seeing not only the double click, but we were observing some weird signal on the detectors. We were seeing that the signal was sometimes fluctuating a lot, and it was if the detectors had more photons, this one has left, and this detector has more photons, this one had less photons. And we were seeing that, and we were like, what's going on? But when we were looking at the double click, it was okay, but this was weird, and we didn't understand, and we were like, okay. And then some of my postdocs, Carlos Anton and Juan Loredo, did another measurement where they started to see something similar, but in a different settings. And then suddenly it was like, yes, we know what's coming, what it is. And what we understood is that actually the dot, you can ask it to emit a photon, but actually you can also have it emit half a photon.
Oh my God, I know where you're going with this. With Carlos, he tried to explain it to me and I was like, oh my, this is...
Yes.
Please, okay, Pascale, please explain it to me because with Carlos, we spent like 15 minutes, just me asking, okay, let's try it, please.
Okay, I'm going to try to make it simple. There is a very fundamental physics phenomena that is called coherent control. So it just said to have your S2 level and you send the laser. And when you send the laser, you bring the atom to the excited state, and then it comes back, etc. But you can actually stop on the way. You can stop in between the 2 states. You switch on your laser, and your atom is in a ground state plus excited state superposition, quantum superposition. Okay, so your atom is in a superposition of quantum states. This is the basics of this quantum revolution. But then when you let the atom emit a photon, if it is in the ground state, it doesn't emit a photon. But if it is in the excited state, it emits a photon. And then basically, if you let this atom emit a photon, what you have at the end is not 1 photon, but it's a superposition of having 1 photon or not, and not. So it's not half a photon, it's both 1 photon and no photon. And I love it because what I love about this story, so it's cool that Carlos told you about it because we both love this story, is that what I want to illustrate there is that first now we have plenty of ideas with this kind of stuff. But also, what I love is this, what we call serendipity in science. Some things happen. So there is some signal, you don't understand it, you can choose to disregard it. But if sometimes it hunts you back and you start to think about it, and then suddenly you understand what's going on, this is a fantastic feeling. It's just, oh, we want something new, it's beautiful, it's fun. So this is part of the I wanted to share that because these are stuff that are not expected, which are a fantastic surprise. And I feel sometimes that in all my research paths, I can tell you I did that because I wanted to do that, etc. But at some point in the stories, and then suddenly there was something new that was unexpected that actually changed everything. And researchers not often say that, okay, there was a kind of a moment that was unexpected, it was strange, different, and it changed everything. And it's not that we have planned about it. And this is what is beautiful about fundamental science, because if you think you know what you're going to observe, you're not doing fundamental science, you're doing something different. Okay?
Yeah.
And these kind of moments in your career are so cool.
It's ridiculous how amazing, beautiful, and fantastic this concept of quantum superposition it is. So there is a photon, but there is also no photon. Yeah. So it's almost like a Schrodinger's cat.
It's kind of Schrödinger cat, yeah.
Oh my God, this is, oh God. Okay, I won't say that I understand it completely right now, but I'm gonna keep asking questions and it's so cool. I can imagine why you picked this as one of the research projects that is closest to your heart, because you covered so many in the questions before. This is brilliant. So, Pascale, it's clear to me that this fascination of doing the research and the fundamental research and also the tech or the engineering sort of research is really fascinating for you. And also there is the teaching and everything as well. So as a scientist, you are doing more than just the research, and you are the perfect example of that. So other than the research aspect of being a scientist, what else do you love about being a scientist?
I love being with other young minds and brainstorm with them. This is what I love the most. I love the most supervising my students and interacting with my colleagues and having these things where we are looking at the data, we're thinking of the next measurement, and everyone is coming in with some insight or ideas and stuff, and something grows. And I love this idea that, so I'm getting older, and sometimes you come just to have just a tiny idea. You think, it would be interesting to investigate that, to give that to a student, and then boom, it's a beautiful plant that is growing. It's amazing. And the human adventure in all that is probably that gives me the strength to do that all day, because I cannot lie, it's very tiring, all this. And the beautiful part is really these interactions and this stimulation, this constant stimulation of mind. And it's like, I don't understand, I want to understand. Oh, it's so cool. And this learning process that never ends is just... I should say that I didn't feel always like that. I think I want to say that because young scientists can feel very intimidated by that. At the beginning of my career, it was like very scared of going to conferences. I was always thinking I'm dumb. I don't understand. And yeah, sure, I was always feeling very insecure, and that I didn't dare to say, "Whoa, I have no idea what you're talking about." It's not easy to say, "I don't understand. Please explain me better." And you can also meet in the communities people who are like, "It's obvious, I don't understand your question." Actually, these people who say that are mostly the ones who are not the best at understanding themselves or explaining themselves. Because if you explain well, it means that you understand well. Anyway, what I wanted to say is that I've not always been this enthusiastic, confident person that was like just going there and having fun every day. I had a lot of years of doubts, hours. And I remember very well during my PhD and my first years as a CNRS researcher, when I'm going to open a tea room, I'm tired of this. Giving up. Woo! I'm tired of that. And then you hang in there and it becomes easier and it becomes more and more fun.
It's hard to imagine that you were, and I believe you, but it's just hard for me to imagine that you were this, not shy, but doubting yourself, insecure to some extent even. I can't imagine.
Because I'm not anymore, but I have young daughters, 20, 25, and they are like that, and they are bright, and they are still doubting themselves tremendously. They have students that are just like that, and it's often more women than boys, than men. This notion that you are not at the place you should be it's very common feeling. It's also for men, but I think it's much more difficult for women.
It's also the societal thing and the way you grow up. It's not because of, it's not just like men and women thing. It's more if men also were grown up in a society that is telling them to doubt themselves in other aspects of their lives, then it's a human thing. Absolutely.
Yeah, in quantum technology, there were 20% of PhD students who are female, but at my level, we are maybe like just 5% left or 10% left. So it's a very few. And it's hard to have some kind of model what it means when a feeling of you are in the right place.
I agree. Thank you for voicing that. Thank you for sharing your experience as well. A bit more on the lighter side now. Let's go a little on the lighter side. Sounds to me that your experience, other than probably at the beginning of the insecure or like imposter syndrome, your research experience has been wonderful. Of course, I only got the highlight reel in the last, let's say, 90 minutes that we have been talking. But if you have 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here, okay? You can ask for a trip to Mars. You can ask for a coffee machine. I don't know. I can't imagine what you don't have. But if you have 3 wishes...
I want a twin of myself to have one knee resting at all time.
That's a good one.
Okay, yeah, I want to just replicate myself. That would be fantastic. So that I don't want to miss any of it, but I still would like to have some more free time. That's for sure.
That makes complete sense. 2 more to go.
Well, the other one I would say that, so it goes, it's the same. It's not another one. It's the same. I think we should change the rhythm. I think everything is accelerating. I think it's a society stuff with all the communication tools and all that. So everything is always going too fast or even faster than before. Science is exhausting because you need time to think. You need to stop, look around and think to have new ideas. It's impossible to run and have new ideas at the same time. Nobody can do that. And I would say that in the COVID time, when everything stopped, to some extent, there was something fantastic about it. We were finally given time to think peacefully on what we are doing, why we are doing, where we want to go on the research, new ideas, and actually it was extremely fruitful. So this pause button that happened during COVID, I'm thinking, okay, that was dramatic, it was terrible, but to some extent it showed us that we are always running and it's not good for research. The next wish, and you mentioned the Presidential Council, I accepted to be there because there is such a gap between politicians and scientists. Also during COVID, it was very obvious that nobody trusts science anymore. It was just crazy. And this is really important at our time with climate change and all that. And so I accepted this position because of that, the idea that we would meet more often and we would get used to each other's world. I also was very interesting because politician has an impossible job to do. It's crazy impossible. But if there is more trust between politician and scientists, I think we will be more creative on the science side.
Absolutely. And that's the second week.
And the last wish is that there would be less gender bias in the science in general. I managed to go through all that. It was okay. But we all have experienced women in quantum. We have all experienced kind of stuff that are really not cool. And it would be easier if we had some kind of advanced, more balance. And actually, at some point, it was the magic of some moment. My group was for 3 years completely gender balanced. It was amazing.
Wow.
It was fantastic. and I cannot really spell out why it was different, but it was different. And it actually changed the dynamic. It was really cool. And I think we all enjoyed it. And I think it's coming back again because at some point we went back to 0. Yeah, it's hard. COVID didn't help either. Yeah. So that would be my 3 wishes. But I think the most urgent one is the first wish.
The first one, to have a clone and have this change of rhythm. For, again, it all comes down to the advancement of science and research. All of this is just coming to that. But yes, all 3 of your wishes are for the betterment of science, for the betterment of the technological advancements. And a clone. That's what I was wondering. That's why I asked you at the beginning of the podcast, like, how many hours do you have in a day? But it's fascinating.
I cannot complain. I love it. But it's not a rhythm you can sustain for so many years. That's for sure.
That is for sure. I can't make all of your wishes come true. No. I think you have the power, more power than me, to make them come true. Yeah. But I hope that once we are putting it out in the universe, then it happens.
Thank
It
you.
happens. All three of your wishes, absolutely. This has been fantastic, Pascal. This has been wonderful. But one last question. You will also be taking over the Real Scientist Nano Twitter account, you and your team, which has more than 3,400 followers. So can you give us a snapshot into what is coming in that 1 week?
Yeah, so when the source comes here, we will have this, you will offer the possibility to have a vision of what's going on in my group. So it's a very international, diverse group. We have many research topics. So we will organize so that our each PhD students explain a bit with simple words what we do. And we'll try to show maybe also the connection between what we can do at Quandela, what we do in the lab. And I'm hoping that we'll have time to test the source, to do an experiment with the source as an illustration. It could be like, maybe we will show how we can do some communication protocol. Let's try. I'm not promising
That would be perfect.
but we will try.
Yeah, we will try. We will look out for all of that. Thank you very much, Pascal, also for being so generous with your time. Thank you. Thank you very much.
Thank you so much.